Okay, thanks everybody for rejoining our session. First thing I'd like to do is I think we had a fabulous session with our presenters. I'd like to really thank everybody who submitted an RFI input and presented today. I think we had so congratulations to all of you. I know it takes a lot of time and energy to put these together, to write the paper and submit them, but there's some really good ideas that we can use. So thank you very much for participating today. I'd also like to thank, before we get into talking about the different topics that we'll kind of cover, I'd really like to thank a few people that made this session possible. I'd like to thank Mark McDonald, who led our CAT team, Joe Gard, who helped look at all the RFI submittals, and Pedro Lopez, who isn't here today, Wendy Watkins for helping support the session, Alma Stephanie Tapia, who's tried to keep me straight for this whole workshop and for many other things. She's helped organize our session today. Carlos Westel, who's helped build the charts, and all our other team members back in Houston that have really helped make this possible. So what we're going to do is, hopefully we'll make this a little interactive, but we'll try to talk about a few of the different topics coming out of today's session and where we go forward from here. We really see this in a couple of different frameworks. So these are the building blocks that we use that I talked about. We were really trying to make this mission very affordable, very lean, and just use the bare bones capabilities for Orion. Today, you guys have presented some amazing ideas of how we can move forward. We'll talk about things under 4 different areas: extensibility for exploration, anchoring techniques, translation and tools, robotics, and additional mass delivery for utilization. The way we kind of see the mission, for those of you that are familiar with the Global Exploration Roadmap, today we have the International Space Station at the top row, and we're doing amazing exploration work on board the space station, closed-loop life support, habitability, human health and performance. The next phase is this asteroid redirect mission in the next row, where we'll do some exploration of that asteroid in 1 or 2 missions is kind of the concept. Those sort of feed into an extended duration time frame in cislunar space. And many of the ideas that we've talked about with enhanced robotics, with modules to extend our duration in cislunar space beyond what Orion provides, those are the things that feed into that kind of realm, that lunar vicinity, cislunar space. We'll sort of use this as a staging point for sort of building up for exploration. And then the Global Exploration Roadmap shows the next phase of other partners who are interested very much in the lunar operations. It shows a path there that NASA would support those operations should another partner decide to pursue that. And then, of course, our ultimate destination on the bottom row is sustainability toward Mars. And so the things, when we talk about what capabilities to pursue, we need to keep in mind the end goal of Mars as the destination, and also these other paths in cislunar space. So what we want to do is take the initial mission, which is, we agree, is a very capable mission, but very, very simplistic, and sort of build upon that with the things we've talked about today. So here's kind of a notional path that we might be on, and this is our concept of extensibility, sort of in the near term. We would fly a couple of missions, testing out the Orion capabilities, and then we would fly maybe this ARM mission to the asteroid. You can see the robotic spacecraft in the upper left, and then we would bring Orion up, and then we sort of see this next phase as extended operations in cislunar space, where we might have a habitation module of sorts. We show a node-like module, but Boeing and Lockheed had really good ideas as well on how to extend that capability, how to do different things. Perhaps that module is an international module, as Mike Rafferty showed in his presentation. And then we showed, maybe there's some resupply vehicle on there as well. And then there's sort of a path as we build in cislunar space. Then we can build toward a Mars deep exploration capability, or maybe some lunar excursions to work telerobotics with the lunar surface. So there's sort of a path that supports the Global Exploration Roadmap. We've had to work hand in hand with our partners through this process. So this is just sort of notional of how we sort of see it. In the workshop today, we've had a lot of really good ideas on extending Orion capability beyond what it's designed for, which is 4 crew, 21 days. We thought that the pantry idea was a really great idea by Lockheed to try to extend that capability, and in a relatively simplistic approach, I think we would have to work on launch mass and how that mission would be executed to cislunar space. With our early Block 1, we have very good capability, but we'd have to look at that carefully. The pantry is pretty unique and innovative in that we could stow in some additional EVA hardware, additional food to extend that duration, and just use Orion. So it looks like it would be something we could study and be pretty affordable. Then on the lower left, we see the Boeing approach, which shows maybe more extended capability using a node attached to the ARV, which is a very similar concept to what we've looked at as well, and trying to extend that operations in cislunar space. So we think that feeds forward very well and something that we'll continue to study. And then, beyond that, there was some really good ideas relative to robotics and how we could extend the capability and provide more capability from MDA, from Goddard, from ATK, and from several others on how we could maybe extend that capability. That really augments the asteroid mission. It provides, extended capability. We'd have to mature the suits along with that. Today, the suits, as I talked about earlier and talked about yesterday, the early suit capability that we're employing is a very limited capability, and so we'd have to expand our EVA capability to utilize some of these robotics. And then at the bottom, again, we see a nice concept with another, perhaps an international partner module extending operations in cislunar space. So we really see this as a series of missions, not just one initial mission. We've talked openly about the first mission a lot, and we've worked on that at the conceptual level. We really need to kind of string together some sequence of missions. And I think I'll pause here to see if there's any comments from anybody in the audience in our panel today relative to extensibility, whether Mike or somebody wants to comment on extensibility.
If we can talk a little bit about the sequence of missions concept, that seems like a really important concept, and it's difficult not having a firm destination set for after asteroid, but maybe there's ways to look at capabilities in a sequence of missions that feed forward directly to Mars and have direct applicability to that kind of mission as being maybe emphasized. And it seems like that would tie in with the GER. What are your thoughts about that, Steve?
Yeah, I think we're sort of looking at, how do we tie together, how do we start with this mission and then build upon that in a sequence of missions that gets us to Mars, and what would those missions look like? What would the propulsion system look like? How does the solar electric propulsion feed forward? How do the solar array technology feed forward? All that we think, lines up very well with cargo delivery to Mars, and so some sequence of launches. We think cislunar space will be an area we'll operate in for some period of time as we do the build-up, just like for an International Space Station. There was some sequence of time where you're building up, but we agree, Mike, that there's some period of time where we're going to be building up a capability in cislunar space and as we begin to move out toward Mars. See, there's a comment here in the room.
Wendy?
I think you said it well, Steve. By looking forward, that's really the focus of where human exploration is going on to Mars. And I think we kind of, although the asteroid mission is very important, we think of that as a stepping stone to going further. So keeping that in mind and making sure that things for the asteroid mission are proving out that next step is crucial, and doing things that are extensible in that regard.
I agree. We see the asteroid mission as a nice foundation where we get those early capabilities, docking, EVA, and then the solar array and solar electric propulsion, and we can operate relatively close to the Earth. It's much further, 10 days or 12 days away relative to where we're at with Space Station, but it's a kind of a stepping stone approach. I think Ben has a comment.
Yeah. I would say that, and I know you're doing this as well, but just to let the public know that not only destinations, where are we going to go next, but just sticking around, there's still lots of very meaningful work that the crew can do in orbit that robots can't do by themselves, like assemble very large observatories. So I think as we develop the capabilities here to stay out there longer, to have advanced techniques for EVAs and robotics assembly and manipulation of goods, that lends itself extremely well towards a meaningful goal for the public and NASA, and that is the assembly of science missions that could not otherwise be done. Right? It is enabling to science. And I think that's one of the things that made the Hubble mission so successful for everyone, is not just that we did neato engineering things, but we rewrote the textbook 2 or 3 and 4 times over with the science that Hubble did afterwards. That was only possible because of the crew. The crew and robots working together to change out those instruments and to do the repairs, the unplanned tasks. That, I think, is one way that NASA can, recapture the American spirit and support, is by doing meaningful missions like that.
Thanks, Ben. And we think, too, I think Chris Moore said it best probably last night when he talked about the asteroid mission being unique. I think we in human spaceflight think of the piece parts about robotics and EVA, how we would collect the samples, how we would dock and rendezvous, but the power of moving a heavenly body from an orbit that it's been in from its inception 4 billion years ago to a location is very, very powerful as well. So we think that is a big selling point for the mission as well. How about online? Do we have any?
Yeah. So they were just wondering if you wanted to comment on how the asteroid mission actually extends into other destinations.
I think I'll let Mark do this.
Okay. There's actually several ways that the technologies that we're investing in today directly apply to future missions. The most easy example is Orion. The reentry speeds that we demonstrate on this mission are the same reentry speeds we would need for any lunar mission that you would want to support international desires. But based on your mission design, it can also support missions further into deep space and is a stepping stone in proving out the technologies necessary for Mars entries. Additional technology development would need to be done on the heat shield for that, but this would be the fastest reentry that we had ever done. So the second thing is the EVA suits, which Steve mentioned earlier. The PLIS suits, the portable life support systems for this EVA, would be exactly applicable to a lunar surface EVA or any deep space EVA. With minor modifications, the same life support system could work for a Mars surface thing. So that would apply as well. Microgravity suits for all of the robotic crew interactions. In a second step for logistics, we could bring up additional microgravity suits to augment our initial capability, and this would be a stepping stone for that. Solar electric propulsion on the robotics side. When you look at the efficiencies of solar electric propulsion compared to chemical propulsion, it's dramatic. So having a 40 kilowatt class tug is not only applicable for reorienting the solar system as Steve describes, but it is an extremely effective way of delivering cargo to a cislunar base, all right, for observations or whatever science you chose to do. If you wanted to support an international mission to the moon, that could be a tug to support an international mission. And for Mars staging to deliver Mars elements to Mars, it's a technology stepping stone of increasing our solar array efficiencies and the ability to do large-scale solar, stepping towards the capabilities we would need for Mars. That's actually the beauty of this mission, is that everything we're doing applies whether or not the asteroid mission's there. It's a very flexible technology place that can support lots of missions going forward.
Yeah, I think Mark said it very well. And in terms of suits, Frank, we have traded umbilicals, and when we looked at those, not only are there technical challenges with long umbilicals, you need more consumables actually, because typically you're pumping that the oxygen that the crew breathes overboard. But if you look at how does that feed forward to Mars, we need a suit that's independent of a vehicle to traverse the Martian surface someday, and then maybe as our structures grow bigger and bigger, if we're doing a repair of some sort or some kind of a science experiment outside the vehicle, those kind of things don't feed forward. So when we look at EVA technology, we're trying to look for, a suit that then takes us forward toward Mars as an evolutionary path. Does anybody else have any comments? Got one from Aaron.
Yeah, so on the topic of the extensibility, I think the destination drivers are one axis to look at it, but as Mark was saying there, you know, there are sort of capabilities that you want to get into the portfolio, and so maybe there can be a little bit more discussion. You know, the commercial interests seem to be focused on ISRU and whether that's part of the capability suite that we need. Also, a lot of the talk today was on human-robot interaction and cooperation, especially as you lose ground support as you move further away, or at least the sort of imminent or, you know, real-time ground support. Maybe there are some more as well, and this could prove kind of as a not only a destination but also a technology incubator of sorts.
Certainly, the asteroid is a potential for in-space resource utilization, where we would learn to utilize. Today, in human spaceflight, we have taken every single pound of tool or food or clothing, water, air with us on every single mission we've ever executed from the very beginning. We need somehow to move away from that paradigm. Perhaps this asteroid would be one area where we could test those kind of things, and I'll see if Mark has anything to add.
So it's my job in the technical lead. I've got to look at from a step back. So when we talk about adding capabilities, regretfully, every capability comes with the mass penalty of delivering it there. So when we look in this first mission, as Mike described, you've really got to look at this in a series of missions. So if we want to do ISRU, greater science on the asteroid, whatever capability you're talking about, the first question I have to ask myself is, how are we going to get it there? So in the architecture the way it is now, with the base performance of the SLS and the Orion, very flexible platforms which enable this mission that they were never designed to do. But we don't have significant extra mass to bring up the mass power resources necessary to do ISRU. So that's where things like providing opportunities to commercial logistics to deliver extra mass, things that point us to a node where you could dock a commercial logistics module and an Orion to aggregate new capabilities, long-term life support for Mars, closed-loop life support, or ISRU. So all of those capabilities lead to enabling commercial participation through logistics supply beyond LEO, and potential international or commercial development for node-like things to, you know, aggregate multiple elements. Those in themselves are techniques we need to go to Mars. We need to be able to assemble vehicles in deep space, those types of things. So all of those capabilities play together in an integrated architecture, moving us as a stepping stone towards Mars. So all of those things will play out as we go forward.
Stan, did you have a comment, or no? Any other comments on extensibility? I think we're in, the community is in general agreement that we need a sequence of missions. I think the community is in general agreement that cislunar space is the next logical destination. I think the community is in general agreement that this asteroid mission is the next best step for the different capabilities that it brings to bear, and it's sort of our job across both NASA and industry to build that plan of how then we feed this forward to Mars and talk about it in a way that shows that this is indeed the right path to be on for the times that we're in, for the capabilities that we're building. I think it's a great mission from a sense that it leverages a lot of the things that we're doing today and then builds toward the future at the same time. So we just got to explain that story, put together the kind of the sequence of how that might work, and then talk about it as a community to make sure that we're all sort of in agreement in the direction that we're heading. Okay, the next topic is anchor techniques. I think we saw a lot of innovative approaches to anchoring that we really hadn't thought of and hadn't spent a lot of time of. You know, we have spent time using more traditional techniques of some simple booms on how we would anchor. The JPL approach, this robotic vehicle that anchors upside down, was pretty incredible. I mean, potentially this is something we could look at maybe as down the road after the first mission, something we deploy that could then traverse around on an asteroid and then do some kind of experiments in between the human visits. I think this is a great capability. All the other anchoring techniques are things that I think, need to look at. Most of what we have been focused on is not necessarily having the crew, since we're talking about for the reference mission, a 10-meter diameter asteroid, we hadn't really intended to have the crew actually traverse on the asteroid. So our thought process was more of anchoring from a simple boom, or in more evolved missions later on from a robotic platform. But many of these anchoring techniques are very interesting and may feed forward to the Mars surface or other destinations someday. So I thought there was a lot of really good innovative ideas. I think the problem on the anchoring can be given the different consistencies of the asteroid, from a solid rock material to maybe a looser material or even a rubble pile. That's when the anchoring techniques become problematic for smaller bodies. But for there were some really good ideas. Does anybody have any more comments on anchoring techniques? I mean, I think that's something we need to look at. It's something we'll feed forward. There's a question online. Go ahead, Joe.
Joe?
Yeah, there were a couple of online questions. The first one was actually to Aaron Parnas of JPL. The question was, any worries about the broken claws creating any kind of a sharp edge hazard to EVA crew members?
Could you get Aaron the mic, please?
Thanks, Dan.
I do think that is a potential concern. I know that there's a lot of thought put into how tools are made to prevent, tearing the suits, and I'm sure that the asteroid itself presents somewhat of a hazard if it's a real sharp kind of rock. So that's something we would have to take precautions for.
Joe, what else you got?
I don't know if Jonathan Robill, sorry, I'm sure I'm saying that wrong, of Honeybee Robotics is still online. Jonathan, are you there?
Yeah, and I should have said earlier, this is an opportunity to, if somebody had a question as we work through these different topics, to go ahead and ask the question as well as we talk through them.
Go ahead, Joe.
Yeah, the question was, he mentioned the need to thoroughly test drilling in advance of the mission, and the question is, and it perhaps could apply to Aaron as well, how would you go about doing that kind of testing on the ground?
You want to take a swing at that, Aaron?
Sure. So for our hundreds of K sort of development, we test in the lab just at different gravitational orientations. The ISS is a great platform to try and test some of these at true zero gravity. That would be one pathway. Some of the zero-G flights and drop towers and things offer windows of adequate testing, but probably not enough to really do the work you need.
Well, and that actually leads to another question related, which would be, how do you manage the dust and debris? Make sure that when you're doing drilling and that kind of thing, that you're not creating a hazard for a test on ISS, for instance.
Yeah, I think if you're up on ISS, you need to have sort of full containment. You do it inside of a FRAM or some kind of closed cargo locker. There are also options to use software to use the kinds of robotic arms that Ben presented on to simulate zero gravity with larger robotic arms that are have the dynamics built in. So that could be another way if we can close the loop fast enough.
I think Stan had a question or comment.
Yeah, just a comment. I just want to underscore the importance and difficulty of this branch of our work here. It's very, very hard. You don't know from first principles whether an asteroid you go to is going to be as solid as a block of cast iron or as fluffy as a bunch of beanbag chair filler. If you've ever opened up a beanbag chair, you know what you're dealing with there. So your anchoring could be as simple as a magnet. If you're talking to a block of nickel iron, you can just use a magnet to hold yourself on, or it could be that you cannot do anything with it mechanically and you have to put the thing in a bag. So this is very difficult series of problems, but on the other hand, it means that there's opportunities for a lot of valuable future work.
And I think maybe, the solid asteroid drilling into that is probably maybe the hardest case in some ways, because you've got to penetrate a very hard object. I think we have good ways to simulate that on the ground. Maybe getting into different consistencies of asteroids are maybe easier, simpler tools. The thing then is to keep the crew protected from liberation of material. That's probably the biggest challenge, and getting dust on the suit as well.
So I have a comment to echo on that, and I share Stan's frustration sometimes. I keep asking all these scientists, what's the surface like? And you get every different answer. And the exciting thing is this is the sort of the beginning, right? And we have a sequence of missions already in line that are going to go to these bodies. So we learned a lot when we got pictures from Itokawa, and we have OSIRIS-REx on its way in the next cycle of missions, and we have a Hayabusa 2 mission that may be going as well. So we'll start to learn what these surface properties are. So if you're tying in the anchoring to some of the extensibility, hopefully we won't be dealing with such a wide range of uncertainty in the future.
The one thing to keep in mind in this mission also is that the asteroid robotic vehicle is going to get detailed imaging and sensing of the asteroid when we capture it. And then during the time it is towing it back to the DRO, we will have a few years to plan out our detailed DVA and adjust our tool selection based on that.
That makes good sense. Also, the more we can get pictures of near-Earth asteroids and start building up a statistical understanding of what the population is like, that would be good. I've heard discussions from some of the private companies that they want to go out and start prospecting asteroids. That's all going to be very valuable information. I think from the technical standpoint, anchoring and drilling on a rubble pile is probably going to be our biggest problem. It's going to be very, very hard to deal with what's essentially a cloud of stones, where individually they're very hard, but they have almost no cohesion with one another. It's going to be a great technical challenge for us.
And I think, as engineers, we all like to give me the design parameters and I'll build the perfect system. And remember, we're about exploring, so sometimes we may have to have a couple of different approaches, and we may have a little bit of the unexpected when we arrive, and that's okay, because the reason we're going there is because we really don't totally understand asteroids very well, and we want to learn more about them. Any more on anchoring techniques? This is wonderful. So translation and EVA tools, we've talked quite a bit about this, and this kind of is a good segue from anchoring. Knowing the asteroid is important. We've talked about that. I think there were several promising drill kind of ideas that we will go look at. The idea of taking something that works with our pistol grip tool that we use for EVA is very intriguing. Something that's fairly lightweight. Maybe we could modify and go take a core sample if it's a more solid asteroid. I think we have to think a little bit more about what we do for these rubble piles. How do we get the sample, but yet enclose it in a way we get it and not then have a bunch of debris on the crew and exposing it to Orion and the hatches and so forth. So we need to work on that. I think we've got a lot of good ideas to go choose from there. I was very intrigued by the presentation from Rob Mueller, who I don't think he may have departed early, but thinking about maybe some simple way to get the dust off the suit. Maybe we need to do a little more testing with those materials, and we can work with Rob on doing that, and maybe some shapes that are different than we do a lot of very simple tests in the lab on a very flat sample, but the suit is not very flat. There's a lot of curves and contours. So how would that system work to retard dust? Dust was a huge problem during Apollo, and for a solid asteroid, I don't think the dust would be much of a problem, but for these rubble piles, as we talked, those would be very, very challenging. And then the suits and tools, great presentations on the different kinds of tools, from RRM, the wire cutter, the tools that ATK talked about, and then the drill. We've got a lot of good things to build upon. We've talked some about this, but this is an area I think we can leverage this session pretty heavily on adapting and building different kinds of tools. We've started some of that work in the neutral buoyancy lab, but this is kind of a good time to have this session and get some input from the community on the kinds of things that we could go build. Any discussion on tools, Michelle?
So just one thought is that there were ideas presented with, I would say, some traditional tool concepts. And then a couple I saw that reminded me that there have been conversations about the low-density asteroidal surface potentially requiring standoff distance with the crew, and that there may be advances in some of the remote sensing techniques that actually could be used at a standoff distance that would both take advantage of what the crew brings to the table, but also provide additional protection, especially if there's a bag and you open it and you don't really know exactly what's going to happen when you do that. Anyway, so, I mean, that was kind of an interesting contrast in some of the ideas that were brought forward. That might be something we need to look at a little bit.
Then there was the one KSC concept as well that was kind of intriguing, where we had the device put the pneumatic kind of sound device on the shovel. Maybe a shovel may not be quite right, but something akin to that might be worth looking at.
One step back, I'm sorry.
Go ahead.
One step back from the actual tool as end effector is the interface to the crew member or the robots that are manipulating those tools. And I know there's work going on at DARPA and things like this to generate very effective designs for adaptable tool interfaces. And, you know, as we look at the overall architecture, we should be looking at the architecture of interfaces between interchangeable parts and make sure that we get all the functionality at those interfaces that we need so that they are extensible as well.
That's a good point, Frank.
Alma?
I think Stan has a...
So while that Mike's transitioning to address one of Michelle's comments, one of the things we've discussed that we didn't get out in the video, so this audience hasn't seen it, so I'll describe it, is when you're worried about particulates coming out from a drill or, you know, contamination coming out to the crew, so how do you contain that? And you combine that with a bag. One of the advantages the bag offers with a rubble pile is that instead of just cutting open the bag, you could install effectively a portable glove box over the bag and then cut the hole in the bag to provide containment. So we've talked about deployable tents, you know, to where you would affix those to the bag to provide a barrier between the crew and the particulates, and then have your drill going inside that tent or inside that glove box to contain those types of things. So some of those concepts have been discussed. One of the things we've discussed tools, and we've discussed getting the astronaut to the work site, but how you set up the work site preparation in terms of a glove box or a tent or debris shields, that type of thing, is something that can mitigate some of these risks we're talking about.
Yeah, and I think that's one area that we could use the community's help on if there's ideas about what's the best approach to actually, you know, get into the bag or get next to the asteroid. We like the bag concept because it works for the wide range of potential kinds of asteroids that may be anywhere from a rubble pile to but those, we're still in the process of figuring out what's the techniques, and so the community has got a lot of experience. We showed a lot of pictures from shuttle flights that I remember where we came up with really innovative things to go repair blankets and other things. Solar arrays. This community could probably help us think through some of those things as well. We'll let Stan, and then we'll...
And Steve mentioned the Neutral Buoyancy Laboratory, and I'd like to amplify that a little bit. The NBL, the underwater environment, works for training people and developing tools and techniques for working in zero gravity. Full stop, end of sentence. The orbital environment, zero gravity outside a spacecraft, is probably about the most unnatural environment you can possibly imagine for a person to work in. And the Neutral Buoyancy Laboratory does a great job of preparing people to work in that environment effectively on their first time out the hatch. So that's a resource that we should not overlook. In addition to that, tools and techniques that we tested in the NBL and then tested again underwater off the coast of Florida in Nemo, looking at exploring asteroids. In my opinion, with a background in spaceflight and in asteroid science, we went from not knowing how to do an EVA on an asteroid to now knowing how to do an EVA on an asteroid. It's that valuable, and all that's available at a pretty low cost. And I think it's a resource that we can make very good use of and be confident that what we develop is going to work in space. A shorter comment on containment. We know that most near-Earth asteroids are not too different from most meteorites, and people are cutting those things apart in laboratories all the time without insane levels of containment. They're basically rocks. So I hope we don't frighten ourselves into thinking that we can't touch these things. Dust will be a problem, but they're not poisonous.
Doug has a comment, I think.
Yes, one area that I haven't seen talked about with regard to tools is actually getting into the containment bag, the capture bag. All the videos so far have just shown the bag already open, ready for the crew member to show up and start working there. But I think there are some competing design principles. On the one hand, making that bag very durable and tough and able to withstand anything that the asteroid can do to it. Then the second is need to be able to get into it quickly and easily. So I could see a need for some kind of tool development there, especially if there's reinforcement to cut through, that kind of thing.
Yeah, I mean, we've talked about the concepts, but we're still kind of working through those. I mean, we've talked about having slits positioned in the bag. Of course, the size of the asteroid will determine the configuration. You know, we're going to design the bag for a wide range of sizes, maybe up to 12 meters in diameter. And so if it's smaller, then you've got folds to deal with. So we got to work through that. If you knew it was solid, you could, I think, take a drill and drill right through it and get the core you want, and then discard the material later. But if it's a rubble pile, then we've got to figure out how do I open it, get inside, access the sample, and maybe some of these tools, maybe some ideas about a telescoping kind of tool that you could get in and collect not only a core sample, but if it's solid, but then, you know, some rubble out of it. Maybe there's some ideas here that we can build upon. But that's forward work. We know that's probably the biggest challenge, and then making the suit, learning how to work in the suit with the tools in the neutral buoyancy lab, which is the way we've developed every spacewalk in the history that at least I've been a part of here at NASA. Is we go in the NBL, we work with the tools in the suit that we're going to be in, try to design the task such that we can position ourselves for success.
The other thing I'll add to Steve's answer on, I agreed with all of that, is when we go to collect a sample, it depends on what type of asteroid we're going to, on what our requirements we would put on the sample container. If it is a rock, as some people describe, then putting it in a baggie and stowing it, you know, would be okay. If it is a carbonaceous asteroid where one of your primary things you want to do is to capture the volatiles in that rock and study the volatiles, you're going to want a hermetically sealed container to contain those volatiles. So there's some differences there that we'll take into account. That's as we peel the onion, as we go deeper into this study, we'll investigate the different techniques and how to do that.
How about online? Any comments from?
Well, there was one.
Yeah, there was a question. It didn't directly relate to tools, but it was there was a question about how the ASIS suit was actually derived as the asteroid suit, and what mods and relevant what mods would have to be made to make that relevant for the asteroid mission.
So I can address that. So when we started looking at this mission, we looked at all the suits in our inventory. We looked at the current EMU, that's extravehicular mobility unit, that's on station. We looked at the exploration suit, and we looked at the modified ACES as a very bare bones EVA capability. We also traded an umbilical EVA versus a traditional, what we've done ever since Skylab, is a PLIS, or a portable life support system based EVA. When we looked at all those different suit capabilities, we knew anytime you do an EVA, you want the absolute best suit, and I would never argue with that. But when we looked at the constraints of the mission and what we could do using Orion as the EVA platform from an affordability perspective of trying to minimize new developments in this time frame, the modified ACES suit traded best because that suit had to be worn by the crew anyway for launch and entry. And we went back and looked at the Gemini time frame, and that suit, that the modified ACES, it's a full pressure suit. It'll protect you from the vacuum. it has heritage all the way back to Gemini, and Gemini did several tasks in that suit. So when we looked at the mass trade and how we would stow the suits in Orion and the things we needed to carry with us, that suit traded best from a mass and performance perspective. Orion has launch mass constraints, and it has abort and nominal end emission weight constraints. It can only carry a certain amount of weight as the system is designed. So we made this trade of we're going to go with a less capable suit for the short term to execute this early mission, and then for the long term we'll keep evolving and go build the exploration suit we really need for the future. That's kind of the trade. Hopefully that answers the question.
Any other questions online?
Any other comments for EVA tools? And
So let me, in case the other technical modifications that were made to the suit were some biasing in the stitching to improve where the natural work site is for the crew's hands to reduce crew effort, adding a thermal protection overgarment to handle the difference of the thermal environment from outside the cabin, modifications of including the Phase 6 gloves that are currently being used on stations. So there were basically mobility enhancements and enhancements to handle the EVA environment different from the suit. Those types of things, the TMG, for example, those material developments and everything else would apply to a future suit as well.
So we're about to make some of those mods to the suit and get back in the NBL as the calendar year turns over, and then try to test out some modifications that the ACES suit, the hands aren't necessarily biased properly. It was designed for launch and entry. We think we can bias those and do even more productive work. We know it's not the best suit, but it'll work for this mission, at least we think, for short EVAs. The next chart I have here is some pretty amazing things that we got out of this session relative to how we would do translation in these telescoping booms. You saw in our animation and our graphics we had a couple of booms, but we didn't really look at. We'd love to have a more capable robotic arm, but from a mass perspective for the first mission, it just doesn't really work out. So some of these concepts of a telescoping boom kind of intrigue us a little bit. We've been struggling with how do we get to different places on the asteroid. Let's say we think we can get to positions near the base, if you saw in our graphic, pretty well, but then if we want to go up a little higher on the asteroid, we're a little challenged by our current capability. But these telescoping booms are pretty simple. They're we suspect they're relatively cost effective, and they may give us that capability. So this is something we want to go take a little bit more look at. We talked a lot about the Canada arm, Dexter, the DARPA Friend arm, and those are things, probably would be not for the first mission, but maybe down the road there would be something we would add. But these telescoping booms are pretty intriguing, and then something we'll go look at a little bit more. We were very interested in those. Something that both Mark and I commented on as we went through the session today. Any other comments on translation aids or robotics as we move forward? Quiet. And then, we've talked about, what do we do to further explore the asteroid relative to things like in situ resource utilization. This was an intriguing robotic capability to maybe look inside the asteroid. Maybe this is something we could think about pre-positioning on a robotic spacecraft. I think there's something we need to talk about. How do we package things? There's been a lot of mass trades done, but as we move forward for future missions, how do we add things that really improve our utilization of the asteroid, or maybe turn it over to commercial industry at some point? And then again, we've got to really focus on how do we build functionality across the modules we've talked about for extensibility. Obviously, Orion, there's going to be some limit at some point. Orion is really a crew transportation vehicle, but it can be used as an airlock for these simple missions. Where do we move? Where do we put hardware in the future? It's probably on some of the modules that we propose, either an exploration module or some of these robotic modules to optimize future missions. We liked the simulation work that has been done at Goddard and things that can enhance the mission. Obviously, Goddard has done a lot of work on the sensor technology as well that feeds forward not only for this mission but future missions. And then, everything that we do, we really need to keep affordability in mind. We have, as the human spaceflight team knows, we need to work within our budget constraints, continue to work on SLS and Orion, and then use this as the first mission for those vehicles. So, in summary, we might wrap up a little early. We had a lot of really good ideas. We're going to take those ideas and go back in our team and use those to approve the mission. Extensibility is very important as we take this mission and build forward for exploration. This isn't a one-of mission, it's a stepping stone to future missions to build upon, initially in cislunar space and then onward to Mars. It very much lines up with the global exploration roadmap, which we've been working hand in hand with our partners, which was released earlier this calendar year. We'll maintain some flexibility in the design, and this is a good time. In fact, today has been what I think is the best interaction we've had, getting a lot of good ideas from a broad source of teammates that we work with day in and day out, and some that we don't work with, and some in academia. And we're going to continue to leverage this team and the work in the future to put together the best mission we can. So thank you very much for attending, and really appreciate the support.
Any comments or questions?
Any last comments or questions from the room?
So we're really looking for recommendations for further work. I didn't really see any here, so I'd like to see that tomorrow morning when you brief out, because we have to write a final report about this workshop, and that's going to be key.
Yeah, we'll put together
That's what we have tonight.
some recommendations. We really wanted to have a discussion in this phase, but the telescoping boom is something we will carry forward. I think the suit dust item is something we'll carry forward. The drill technology and using the PGT with the drill is something we'll carry forward.
Boeing's proposal.
So the extensibility ideas that Mike Rafferty and the Boeing team proposed on how to build upon it is something we'll carry forward. So those are 3 or 4 things that we'll carry forward.
There are also, in the first paper, there were some ideas on partnerships that would be really interesting to explore as well.
Okay. Any other closing
I
comments?
think Steve and I both took some notes on ones that piqued our interest for continued work, and we'll collaborate on that after.
To me, I found it very hard. It's one thing to read the papers. It's one thing to look at the presentations, but it's another thing to hear the presentations in person and see how they're delivered and listen to the ideas and get the exchange. I think we get a better product that way. So, but we'll have some recommendations tomorrow as well, so, for our headquarters friends.
I wanted to comment that I also think that the dust on the suit has a lot of promise, and I want to echo that I do think, though, that there's a lot of maybe materials durability and the fact that it's an electronic material, and take into consideration some of those maybe long-term material certification, things like flammability concerns, as they go forward and do more detailed evaluation on those types of materials.
Thank you. Any other comments? Oh, Aaron has one.
This may be a bad one when everybody's ready to leave, but so I know Space Technology Mission Directorate is playing an active role in the robotic vehicle because they're very interested in forwarding the solar electric propulsion. And the question is whether they've engaged you guys in the crew portion of the mission yet, and if you see a role for them to help support some of these activities or building out some of the future capabilities.
So I can comment a little bit. Yes, they've been very engaged on the solar array technology and the SEP systems and the Hall thruster technology, which feeds forward. We've talked to them about how that feeds forward in terms of the array size, the mass and power that we need. But they are also participating in a lot of different areas. For example, in our advanced exploration suit development, they are a partner in our suit development. They've funded some advanced glove work today. They continue to do that. Human robotic systems, some of the technology that Rob from KSC talked about are actually being funded by the Human Robotic Systems Project in Space Tech. So they're already looking at technologies we need for exploration. I know Chris Moore and Jason Crusand from Advanced Exploration Systems works hand in hand with Space Tech on helping them to define the technologies required that feed forward. They've got work ongoing on in situ resource utilization for various destinations. So they've been a partner with us. We've talked a lot, probably maybe too much, about the SEP, which is really a big factor in this mission. In fact, the SEP technology really enables us to even dream of bringing back these kinds of masses from deep space. But there's other things that Space Tech has been working with us hand in hand on as well.
Any other questions or comments? Joe, anything else online?
Thank you very much. This has been an incredible session, so thanks for all your time, and I really appreciate it. And continue to watch the Asteroid Initiative on nasa.gov, Asteroid Workshop, and Asteroid Initiative. Thank you very much.
Thank you.